It's a great pleasure for us to be with you. I'm Bobby Coates, a professor in the Department of Agricultural Economics and Agribusiness in the University of Arkansas Systems Division of Agriculture. In today's webinar, Dr. Louis Ziska, plant physiologist with USDA's Agricultural Research Service in Beltsville, Maryland, will be discussing climate change, CO2, and food security, challenges and solutions. Before joining USDA, Dr. Ziska was project leader for global climate change at the International Rice Research Institute in the Philippines. Since joining USDA, Dr. Ziska has published over 100 peer-reviewed research articles related to climate change, rising carbon dioxide that address agriculture and food security, weeds and weed management, invasive species, plant biology, and public health. Now, Dr. Louis Ziska, plant physiologist with USDA's Agricultural Research Service in Beltsville, Maryland, on climate change, CO2, and food security, challenges and solutions. Louis, we look forward to your presentation.
Well, thank you very much, Dr. Coates. Thank you all for coming today. I know it's early. I hope you have that second cup of coffee nearby. I want to talk about some of the interactions from a sort of a 20,000-foot point of view in regard to climate change, carbon dioxide, and food security. I also want to recommend that if you don't understand and know who this gentleman is, I would suggest to you that about half of you listening to this lecture right now or watching this lecture right now are only able to do so because of this gentleman. And I'll talk a little bit about his contribution in a few minutes. I want to emphasize to all of you something that is very basic and very simple. Civilization does not occur without agriculture. We would have no artists, we would have no lawyers, we would have no politicians, we would have no dentists, we would have nothing like our civilization without agriculture. It depends on a small percentage of individuals who can grow enough food for the rest of us. Otherwise, we revert back to a hunter-gatherer society. Now, there are many different definitions of food security, but I'd like to sort of give you my own. First, there must be an adequate supply. Secondly, it must be safe. And third, it must meet your dietary needs. So we focus a great deal in agriculture on production, and understandably so. You can't have food security if you don't have food. But other issues, such as the safety of the food and the nutrition of the food, are also important, and in my opinion, don't get the attention that they deserve. Now, if that isn't the case, if food security is not part of your culture, of your society, then the consequences can be dire, and they have been dire throughout the 20th century. It's very difficult, if you have never been hungry, to understand what that feels like. And there have been times when hunger has been so prevalent that cannibalism has in fact occurred. It's not something we think about, but it is something that has been an endemic part of civilization since its inception. And what I've done here in this slide is just to illustrate some of those famines that occurred during the 20th century. The last large famine occurred in China in the late 1950s and early 1960s. If you in fact sum up all of the individuals that died from famine during the 20th century, you would come up with a number of around 60 million. And just to put that number in context, approximately 55 million people died during World War II. So famine, food security are incredibly important aspects in the context of agriculture. Back in the 1960s and 70s, following the end of the Second World War, it was clear that populations were still going up. And there was a concern that the ability of the earth to provide food for those populations was going to be challenged. We looked at, or I didn't per se, but others looked at what was called the carrying capacity, and that is the number of individuals that can be fed from the resources that the earth provides. And this was occurring back in the 1960s. And you can see that line is being threatened by the increase in population. Well, back then we didn't have social media, but we had books and movies and television. So movies such as Soylent Green, books like The Population Bomb, TV shows like Star Trek. This is episode 16, season 3, The Mark of Gideon. Yeah, I am a Trekkie, sorry about that. But all these things were being part and parcel of the concern regarding whether or not population explosion was in fact going to cause a pandemic. But today, there are over 7.6 billion people in the world. So this did not come to pass. Why is that? What happened? Well, when you look and compare food security, a couple of basic concepts you need to understand. The world runs on cereals. There may be hundreds of thousands of different plant species, but 15 of those cereals supply the bulk of human food. And actually 3 of them supply more than 50%. Those 3 are rice, wheat, and corn. We call them the big 3. And when the pandemic was threatening, well, the obvious thing to do would be to add more water to more fertilizer to these cereals. And we did so. And the result was a reduction in yield. What? Well, that occurred because what happened was the grains would get bigger and the plants would fall over. And then this gentleman, whose picture I showed you at the beginning of the seminar, his name is Norman Borlaug. And he came up with something very interesting. He looked at cereals. This is actually one cereal, all the different shapes. This is rice. And what he did is he looked at it and said, you know, that shape on the right, that semi-dwarf shape, that's low enough. It has a low enough center of gravity so that when I provide additional water and additional nutrients, it doesn't fall over. And so I can get an increase in yield. In fact, the increase in yield was almost double overnight. So that previously countries like India that had been net importers of things, of cereals, became net exporters, all in the span of a few years. And this was called the Green Revolution. And what he was able to do is by looking at this, to exploit the structural diversity, the morphology of these different plant species, and do so in a way that enhanced the conversion of water and energy into food. But it comes at a cost, as you might imagine. These smaller lines don't occur in nature. They don't occur in nature because they're small. They get outshaded by competitors. So you need chemicals. You need chemicals particularly to control the taller weeds or to control the insects. So there is a cost that has to be associated with this. But even in spite of that, the fact that there are as many people as there are currently is all due to this one gentleman and his efforts. So you can look at this and say, okay, well, hey, the Green Revolution solved all our problems. This is not something we need to worry about anymore. It didn't really solve them, but it put them on hiatus, and let me try and explain. What I've done here is I've gone to the Food and Agricultural Organization, the FAO, and I've looked at the 10-year averages in population and the 10-year averages in cereal production. I included 8 cereals, including the big 3, corn, wheat, and rice. So from 1960 to 1969, you can see the Green Revolution starting to make an impact. The blue line, which is the population line, in 1969 shows about an increase, an annual percent increase in population of about 2.2%. But look at the increase in cereal production. Man, it's over 2.5%. There's no issue. You're making more cereals than you're making more people. Same in the 1970s, same in the 1980s. Now things start to change. We're starting to only produce as many cereals as there are people. Things are becoming tighter. So you cannot rely on the Green Revolution per se to continue to provide sufficient food for the future. That is not going to happen. Resources are still limited. So just to give you some updates, this is a global production. It's a 5-year running average of rice production, the percent increase in rice production over time from the Green Revolution to the mid-2010s, and wheat production as well. Population has gone down. You note that the blue line is decreasing. It's right now we're about 1.1%. So again, just to give you some sense that our production of the wheat and rice, the major cereals, are just barely keeping pace with population growth. So the challenges to food security are already severe. And then you have to go, well, okay, hang on, there's more. And what does that mean? Well, what about climate change? How is that going to affect us? So let's turn our attention to this for a moment and give you sort of a brief overview of what climate change is. Well, it has to do with atmospheric CO2. This is some of the data from what's called the Keeling curve. It's an ongoing measurement of carbon dioxide from Mauna Loa, Hawaii. It's monitoring at over 10,000 feet, so it's not contaminated by, city buses running by the monitors. This is the background carbon dioxide. And essentially, during my lifetime, the amount of carbon dioxide has gone up by almost 30%. Now, that change in CO2 is very rapid geologically. If you go back in time for the last million years or so, the CO2 concentration has stayed pretty steady between 200 and 300 parts per million. So this change from a geological point of view is instantaneous. It's occurring in my lifetime. So why is that? Well, it's not actually very difficult. If you take a source of carbon, which is a source of energy, and you oxidize it or you burn it, well, that produces heat and it produces energy. It's what makes civilization, modern civilization in any case, possible. So if I take coal or I take oil and I combust it, well, I got carbon and I got oxygen. And the byproduct of that, of course, is carbon dioxide. So about 90% of the CO2 that we produce comes from fossil fuels and cement production, calcium carbonate production, with CO2 as a byproduct. About 10% from land use change, principally deforestation. Where does it go? Well, about half of it stays up in the atmosphere. About a quarter of it gets reabsorbed through photosynthesis, and about a quarter of it goes into the oceans, where as it dissolves, it's reducing the pH. It's making the oceans more acidic. Well, where will it go in the future? And I won't go through all the different models. I'll just sort of give you the two extremes. You'll note this green line here at the bottom. That's sort of what I call the everyone hold hands drive a Prius line. It's wishful thinking at this point. Where we are so far is probably between the business as usual line, this red dash line, and some of the other higher lines. So it isn't likely that we're going to see a huge drop in CO2 per se. We need to, of course, deal with that. We need to look at mitigation, but we're also going to have to turn our attention to adaptation and how are we going to account for that. So the bottom line is that right now, by the end of the century, we anticipate carbon dioxide to be between 600 and as high as 1,000 parts per million. Why should you care? Yeah, who cares? Why should you give a flying fig whether CO2 is 300 or 600 or 700, right? Who cares? Well, a couple of reasons why you should care. One, of course, I'm sure you've heard about. One is warmer temperatures, the indirect effect of rising CO2. Well, the atmosphere consists of various chemicals. The principal ones, like nitrogen and oxygen, we're aware of. But two of the others, one is carbon dioxide, and the other one is water vapor, H2O in the air, humidity, if you will. And we understand that these two are the primary global warming gases. What does that mean? Global warming gas, what is that exactly? And the best way I can explain it is through music. Now, if you've ever played a guitar, you know that if I tune two of the strings to the same frequency, let's say A, which is 440 hertz, so they're both tuned to the same frequency, and I pluck one string, the other string next to it will resonate. It will absorb some of that energy from the first string. That concept of resonance also applies for these molecules, carbon dioxide and water vapor. When they experience heat or infrared radiation, they resonate. They absorb some of that heat. Now, that in itself is not a bad thing. In fact, this is a natural greenhouse effect that allows the surface temperature of the Earth to be livable. If there wasn't any CO2, if there wasn't any water vapor, then the Earth would be much cooler than it is right now. So these are greenhouse gases. These keep the Earth livable. But you can start to see sort of a Goldilocks paradigm here. If there's too much or there's too little, how do you, what's going to happen to surface temperatures? Now, the other thing to keep in mind here is that as CO2 increases, water vapor is also very variable on the Earth. So the temperature increase is not uniform. And of course, in the northern hemisphere, there's a lot more land. Land warms faster than the oceans. In the southern hemisphere, there's a lot more oceans than land, and so it's heating up, but not as much. But between CO2 and water vapor, there's another wrinkle that you need to be aware of. And that is, if you look at the equator, the equatorial regions, the tropical regions, the primary greenhouse gas there is water vapor. So adding more CO2 will, it'll heat things up a little, but it's not going to have a huge effect. Now flip that around. Where is the air dry? It doesn't hold a lot of water, and therefore adding CO2 will have a bigger effect. When the air is cold, it doesn't hold a lot of water. So that's why we're seeing the poles warming up faster than other places. In the deserts, the air is dry. The deserts are increasing. They're becoming more diversified. The drier areas of the world are becoming drier. Also with altitude, as you go up in elevation, the air becomes dry. Seasonally, the air becomes dry. You know the difference between the humidity of summer and the humidity of winter. So we predict winters will be warming faster than summers. There's another wrinkle, which probably has been in the news recently, and that has to do with polar vortexes and so forth. Well, the jet stream is a fast-flowing movement of air that occurs when the cold air of the Arctic meets the tropical air of the equator. But as the Arctic is warming, the temperature difference is declining. The energy is declining. And as something that's spinning, as the jet stream does, it spins around the world. As that energy declines, it's going to start to wobble like a top that's losing its momentum. And as it wobbles, the cold air from the Arctic might wobble down, or the warm air from the equator might come up. And that's one of the things that we're seeing more of. So that's one reason why you should care whether CO2 is 300 or 400. Another reason is plants themselves. And this is one that doesn't get talked about very much, and I think that's unfortunate. Back in basic junior high biology, we learned that plants depend on essentially 4 major resources. They need light, they need nutrients, they need water, and for at least 90% of them, they need carbon dioxide. They don't have sufficient CO2. So adding more CO2 is a source of carbon. It's a resource that makes plants grow more. Well, that can be a good thing. There's some work with loblolly pine going from ambient a few years ago to sometime in the 21st century. And hey, loblolly pine grows more. Wow, that's really cool. That's great. It's a little more complicated than that. Let's ask ourselves the question. Suppose I change a resource like light or water or phosphorus, right? Are all the plants out there going to respond the same way? And I think the answer is no, they're not. So what happens if I look at not just loblolly pine, but what if I look at a forest? And this was done actually at Duke University. I was peripheral to this, but it's, to my knowledge, the largest CO2 study that has been done, largest in area. And it took a loblolly forest, and they put these giant standpipes, if you will, blowing CO2 into the center of the forest. And does loblolly pine respond to that? Yeah, it does. But it's not the only thing that responds to it. In fact, the winner, quote unquote, was this species. And this species is, in fact, poison ivy. So more CO2 doesn't just mean more loblolly pine, it also means more poison ivy. And in fact, if you had to look at it from a competitive advantage, the poison ivy would win. So you have to be a little bit careful when you talk about CO2 as plant food, because it's not the same food for everybody. And when you add more of a resource, not everything is going to respond the same way. So the fact that they are going to respond, however, is a major issue when it comes to looking at how rising CO2 is going to affect all life on the planet. And again, it's unfortunate that this aspect doesn't get talked about enough, but it certainly will alter global plant biology. All right, so we've looked at food security, we've looked at climate change. Let's look at some of the consequences. Let's look at production, and I'll give you a couple of examples in the physical effects of climate in terms of production, but also talk about some of the biological interactions, focusing on weeds, and then a little bit about food safety in terms of pesticide use and so forth, and then a little bit about nutrition in the context of protein. So let's begin with a common occurrence. It's Friday. You've had a long week. You take your family to the local steakhouse. The kids, have burgers. You have a nice 2-pound steak. Your wife has chicken. How much water have you consumed? Just looking at the picture, a beer, maybe a glass of water. But it takes water to grow food, right? So it takes about 20 to 40 gallons of water to make your mug of beer. Yeah. Potato, 20 to 30 gallons of water. Slice of bread, another 20 to 30 gallons of water. The salad, 40 to 900 gallons. And, 900 gallons, why? That has to do with what you put on your salad. If you only have lettuce, it's 40. If you put on cheese and sour cream and tomatoes and ... it can go up to 900. What does your steak do in terms of water consumption? A lot. It takes a lot of water to grow the feed that feeds the cow that provides the steak. It takes, at this meal, you would basically consume enough water to fill an Olympic-sized swimming pool. And agriculture is the primary user of fresh water globally. So it's something to think about in terms of the water issue. And of course, as things heat up, water is going to be in demand. Basically, and roughly, 1 calorie of food equals about 1 liter of water. So I want to give you a little bit of background. My father was in the military. He retired in Southern California. And one of the sort of visual miracles that you see in Southern California is the Colorado River, and particularly on the border between California and Arizona in the Imperial Valley. Where I grew up on the edge of the Mojave Desert, there was no green, maybe a couple of weeks out of the year when the rains came. But man, when you drive down to the Imperial Valley, it is nothing but green. And that contrast between the green and the desert is phenomenal. All of that depends on irrigation water. And what's happened is that as that irrigation water is so important and is becoming used so frequently, that this is the Colorado River before it goes into the Gulf of California. There is no river. All of the water is taken out before it gets there. It's not just the Colorado. Here's the Rio Grande. Most of the water is taken up in the Rio Grande. And we predict that, particularly in areas where desertification is increasing, that rivers like the Indus, rivers like the Nile, are not going to flow to the sea anymore. They're going to be all used up before they get there. So water, in my mind at least, is going to become a flashpoint in the context of food security and climate change. Temperature is another major issue. We know that the average temperature is increasing. That doesn't mean that you can't get below average temperatures. Of course you can. But you're going to get above average temperatures and more in terms of extreme heat. Why is this important in plant biology? Well, because different organs of the plant don't have the same degree of temperature sensitivity. If I look at the vegetative temperature for major crops, that's a fairly high temperature, as high in the mid to upper 90s. But flowering, no. Flowering is in the 70s and 80s, right? Why? Well, because the pollen that the male flower produces is, in fact, temperature sensitive. And as you can see in this lower left figure, the percent seed set doesn't just decline gradually. If you reach a critical threshold temperature, it drops to 0. And this temperature issue is one of the major concerns in regard to damage to U.S. crop yields under climate change. What about dairy production? Well, cows in some ways are very much like people. We have a humiture, that is, we don't like to be hot and humid. And here's some data from the University of Arizona showing the temperature as a function of percent relative humidity. Lower temperatures, lower humidity, there's no stress, but obviously if you go up to 90% humidity and 100 degrees, you're going to get severe stress. And the graph on the right is showing you the projected decline in dairy production for the Northeast based on the business as usual projections. Let's segue for a moment to biological constraints. If you're a grower, you know that it isn't just the environment that's going to affect your production, but insects, pathogens, and weeds are also major concerns. Crop loss, percent loss from weeds in the US, but the can-be control costs are very effective in trying to maintain weed populations and increasing production. So what happens then in between weeds and crops as a resource changes? Well, let me provide you with this true story. And pardon, I'm also a Star Trek fan, so a long time ago on a farmer's field far, far away, there was a farmer who was growing corn in southern Pennsylvania. And this was back in I think it was the 50s. And back then, the cost of fossil fuels was very cheap. It was 15 cents for a gallon of gas. And the fertilizer was very cheap. And so he said, you know what? Here's what I'm going to do. I am going to add so much fertilizer to my field that there's going to be enough for everybody. Enough for the weeds, enough for the crops, right? There will no longer be any competition. And he did. He put out 10 times the recommended dosage of fertilizer for his field. And the end result of that was nothing but weeds. Again, when you change a resource, not every plant species responds the same way. When I change a resource, in fact, whether that resource is fertilizer or carbon dioxide, the weeds can be the beneficiaries. And in particular, the worst weeds, the ones that are similar to the crop, can in fact benefit from both recent and projected changes in carbon dioxide. Well, rightfully you can say, well, this isn't really a problem. We'll buy some Roundup. Not a problem, not a problem. And you know, we do use a lot of Roundup. This is some data from the US Geological Survey. I think the red lines are about 90 pounds per square mile of Roundup, and you can you can look at this and pretty much tell where we grow crops in America. We use about 300 million pounds of Roundup annually. The problem, of course, if you overuse anything, is that the number of species that are resistant to Roundup and to herbicides in general is increasing very quickly. This is some data from Ian Heath, who's a lead scientist who's been documenting this. What happens if in fact CO2 is plant food, it's going to be plant food for weeds as well. How does that in turn affect things like herbicide efficacy? And so we have ambient levels of CO2 on the left. This is Canada thistle, and it did a fairly good control when we sprayed it at the recommended dosage. But on the right, at about 700 parts per million, we had no control, zero control. Huh. So the glyphosate efficacy was reduced. That is a little weird. What's going on with that? Well, it turns out that yes, CO2 is plant food, but again, there's another level of complexity. It doesn't always affect the same parts of the plant in the same way. So here we have the elevated CO2 divided by the ambient. A value of 1 means no effect on the shoot growth or the root growth. But over time, what we found was that the roots really did well when we gave them more carbon dioxide. And the problem with that, if you're familiar at all with Canada thistle, is that it has a very, very extensive root system. And any part of that root system can, in fact, grow a new crop. So what we were seeing, we think, is that as the CO2 increased, more roots were produced, and the same amount of herbicide did not control or kill all those roots, and eventually the plant regenerated. Now, can you kill the plant if you add more herbicide or you add a higher concentration or increase the spraying and so forth? Yeah, you can, but there's going to be a cost. There's going to be an environmental cost. There's going to be an economic cost to that. What about nutrition? Well, when you suddenly change the atmosphere and make it very high in carbon, other things happen. This is the plant ionome, which is sort of a confluence of all the different elements that are present in plant organs and plant material. And this is the, I think, average of several hundred different studies. And the CO2 averaged out to about 690 parts per million. Now, when I give the atmosphere more carbon, when plants take up carbon dioxide, their organs become carbon rich. That's the C on the left here. But what happens, however, is that other elements, nitrogen, phosphorus, potassium, calcium, sulfur, etc., decline over time. And because nitrogen is a pretty good proxy for protein, what we find is that that also declines, with the exception of leguminous plants like soybean and peanut, which appear to not really change very much with more CO2. So I want to talk about some of the work that we did. It was published, I think, in May of last year. Work that we did with Chinese and Japanese scientists, again, using a phase system similar to what I showed you earlier for the loblolly pines, except this is a slightly different system. We didn't, not quite a big an area, but inside the ring where we're blowing at elevated CO2, we have about, I think, 8 different cultivars in China, 8 different cultivars in Japan. And we wanted to compare them with and without additional CO2 in terms of their nutritional content. And what we found is similar to what was found for the meta-analysis, and that is that many of the different lines showed a significant decline in percent protein with additional CO2. Now, these are japonicas and indicas, hybrid lines. These are lines that are currently being grown in those areas. So it's, it means something in terms of the overall nutrition. Other elements like iron were also being affected. Zinc was also being affected. And we chose iron and zinc because they have ramifications for human physiology. And so we wanted to find out about that. And this is the work that came out, I think, in Science Advances in May of last year. But we also wanted to look at some of the vitamins. So we didn't have the opportunity to do this for the Japanese cultivars, the rice cultivars, but we did for the Chinese ones. And so we looked at vitamin B1, B2, B5, B9, and there is definitely a negative impact of rising CO2 on the vitamin concentration of the seed. Wow, that's really disconcerting. And then even more disconcerting was that we looked at another vitamin, alpha tocopherol, or vitamin E, and it went up. So what the hell is going on here? Why are some going down and some going up? Well, we think maybe, there's a firm possibility of a definite maybe, that it has to do with this carbon to nitrogen ratio, in the sense that if I have a secondary compound that has a lot of nitrogen, and that's shown along here along the y-axis. So a value of 0.20 means that 20% of the compound has nitrogen. Molecular weight makes up 20%. The nitrogen molecular weight makes up 20% of the compound. What's interesting about this is that the percent change relative to ambient is proportional, inversely proportional to this change. So if I have a lot of nitrogen, I'm adversely impacted. But if I'm carbon rich, like tocopherol, I might be benefiting from that change in CO2. So we want to do more work on this. And as part of this, we wanted to also look at the bee aspect, the pollinator aspect. There's a lot in the news about this. If it's affecting human nutrition, is it also affecting bee nutrition? Now, bees are really, really good about finding sugars. Carbs, man, they have little dances that they do, you know, they tell their fellow bees, hey, there's a great source of sugar, you know, 20 feet out, hang a left. Not so much in terms of their protein sources. Most of their protein, all of their protein comes from pollen. And it's not something that they have the ability to distinguish one pollen source from another. But if protein is being impacted by rising CO2, wouldn't that also affect bee nutrition? So we wanted to get a handle on this and to see if the recent changes and projected changes in CO2 might be affected. How do we do that? It's really difficult to scrub CO2 out of the air. Well, it turns out there's this thing called the Smithsonian Natural History Museum. And in addition to the dinosaurs and the Hope Diamond, way in the back by the gray metal cabinets are collections of goldenrod. Now, the goldenrod was actually started collecting back in the first ones we found were back in the 1840s, but it has pollen on it, flowers on it. And we can't assess the protein per se because the protein will have degraded, but we can assess the elemental analysis for nitrogen. So we looked at carbon, hydrogen, nitrogen for these different goldenrod samples from the 1840s on to today. So to give us some sense of what's the historical evidence that the recent change in CO2 has in fact affected the protein concentration of goldenrod pollen, one of the last sources of pollen for bees before they overwinter. So it's a critical source. And then we wanted to look at experimental evidence. And this is some really elegant work by Wayne Polly, a USDA scientist in Texas. And these sort of Conestoga wagon looking things here that you see are actually plastic chambers where CO2 is added at one end. And as the plants photosynthesize or remove CO2, by the time you get to the other end, you're seeing carbon dioxide values back 100 years ago. So this was our way of looking at it from an experimental point of view, and thank goodness we had enough goldenrod along these chambers to do this. So basically, here's some of the data. The estimated protein based on the nitrogen concentration from the Smithsonian, and then some of the experimental data from the Texas site. And the numbers are slightly different, but they all show the same thing, that as CO2 changes, has changed, and will continue to change, protein is going to go down. There is going to be an impact in terms of nutritional aspects related to bees. Is that something that other insects might be seeing? Is that underlying some of the reports of the insect apocalypse? Honestly, I don't know. But we'd be very foolish, I think, to ignore it, we need to try and find out more about it and what's happening here. Is it something that's going to continue in a linear fashion? At what point will it start to bottom out? We simply don't know. This is written up in the Proceedings of the Royal Society back in 2016. So just a quick word about pathogens. Some of you, I'm sure, have gotten food poisoning. On average, 1 in 6 Americans get sick by consuming contaminated foods or beverages. And not surprisingly, as the temperature goes up, that's going to affect the degree or persistence of some of these pathogens in your food. So overall, here are some of the challenges in the context of food security that are going to be posed by climate change. Water, number one. Again, I think that's going to be an essential aspect. Floral temperature sensitivity and seed production, again, that's going to be another big aspect. Pest demographics, pest pressures, crop losses, and chemical management are going to be impacted. Nutritional quality. Food safety is going to be a concern, or should be a concern, in terms of looking at some of the aspects of this. Now, we've talked about this so far in a very sort of surreal scientific way. And I often get asked by students, well, what does this have to do with real life? What does it have to do with real events? Well, one of the real events that's happening, you probably have heard about, is the border crisis. You have large groups from Guatemala and Honduras that are coming to the US. Why is that? Well, it turns out that if you look at these areas and you look at the increasing drought index, it's becoming drier. That triangle between Guatemala, Honduras, and El Salvador is becoming drier. It's not to say that the climate-induced change in food is the sole reason, but it's certainly a contributing reason. The focus on violence is eclipsing the big picture. This is from Robert Albro, who's a researcher in Latino American studies at American University. The main reason people are moving is because they don't have anything to eat. It takes a tremendous amount of leverage to stay where you cannot eat. You will move to go to where the food is. And we are seeing a strong link to climate change. I would offer that this is not going to be the first migratory aspect of climate and food that you're going to see. I would urge you to Google things like climate change in Syria, climate change in South Sudan, climate change in Pakistan. It is something that we are going to have to deal with. These are the challenges. How do we solve them? What can we do? Well, if there's crisis, there is opportunity. What are the opportunities here? What can we do to adapt to the change in climate that we are, in fact, seeing? Management, genetics, education, research, ... There are a lot of ways that we can approach these crises. How about management? Well, right now in modern ag, we go with faster, cheaper, uniform. We don't have fertilizer per se, organic fertilizer. We use synthetic fertilizer, which takes a lot of energy. It's part of the Haber-Bosch process. It takes nitrogen out of the air, converts it into ammonia. We grow our corn. We take the corn or soy. We give it to cows. We don't give it to individual cows. We give it to them in what are called CAFOs, or concentrated animal feeding operations. Why? Because they put on weight a little faster there. They can go to market faster there. But there's cost. The cost, as you can imagine, is in terms of cow poop, because that cow poop, when it flushes out to Mississippi and the other tributaries, actually creates what are called dead zones in the Gulf of Mexico, which in turn cause dead fish. So this is not a balanced system. You can look at one part of it and say, yes, it's an advantage here, but it's not an advantage in terms of fisheries down in the Gulf. Polyculture. And I know that's a strange word, but in fact, it's something that you're probably, if you're a grower, your parents or your grandparents practiced. You grew the corn, you fed the corn to the cows provided the fertilizer for the corn. There's its own little mini ecosystem that's being set up here. And for modern polyculture, you can do some things like this. You can have ducks out in your rice paddy. The ducks will, in fact, eat some of the insects. The poop from the ducks is fertilizer. There's, you may lose out a little bit on the rice production, but by changing your diversity, you have in basic insurance. Other farms, other small growers, 10 acres, 20 acres, are growing 15 or 20 different crops, so that any one crop, they're not dependent on any one crop economically. So we're talking about polyculture in terms of space. You can plant multiple varieties of a given cereal. And the reason, again, overall, is looking at it from a yield perspective and a diversity perspective. Now, if I only plant one cultivar and everything goes well, great. But if there's an increase in severe events, if climate change causes more extremes, it's better to put more eggs in different baskets so that you have some fallback position, you have some insurance. And so that's what I'm offering in this overall sort of curve here. Time, rotation is something that farmers understand, but also looking at rotation in terms of animal rotation, or putting in cover crops, or having those cover crops as a means to feed other animal raising and so forth. So increasing resiliency is part of this diversity issue of time and space at the grower level. What about genetics? We have tremendous amount of natural variability in things like apples and peppers and potatoes and corn and so forth. How do we select crops today? Well, our economic driver is very different than it was for our grandparents. I like McDonald's. I like their fries. I know it's a weakness, but you know they're good comfort food. But all their fries depend on one variety of potato. I think 90% of them are one variety. Russet Burbank, nice big fat potato, makes nice big long fries. But if I only grow one variety of potato and the climate is changing, that's not so good. But I'm going to grow it because, hey, McDonald's buys 3.4 billion pounds of potatoes. So of course I'm going to grow it. But this is potato production in the US of millions of metric tons. You can see the Green Revolution part pretty easily. But right now, at least since the beginning of the 21st century, production's going down. Right now, you have to use so many chemicals on Russet Burbank potatoes that they actually have to be put into a large warehouse to degas before they can be used. So that we need to diversify. We need to go beyond that. How do we do that? What do we select for? Well, what about CO2, right? CO2 is plant food. Can we use it as a means to increase yields? Well, this is some work I did with Anna McClung, a USDA scientist in Stuttgart, Arkansas. We did 6 cultivated rice lines and 6 wild rice lines. This is this leaf area, and I think it was at 55 days after sowing. But I just wanted to point out at 300 parts per million, that is the CO2 back in the 1950s, there's a fair amount of overlap between cultivated and rice and wild rice. But at 400 parts per million, the current CO2 level, what we're starting to see is a segregation. It isn't that nature is selecting for the cultivated lines. It's selecting for the wild lines. And if I look at seed yield in grams per plant for the CO2 change that's already occurred, Clearfield, which is a typical cultivated line, shows a little bit of an increase. But the weedy line, the Stuttgart line, doubles. Weeds might be able to provide us with some interesting genetics as a means to adapt to climate change. Now, at present, to the best of my knowledge, there is zero evidence that breeders have selected for CO2 as an additional resource. Surprisingly, or ironically, marijuana growers have. I know that sounds odd, but if you go to Google and type CO2 and marijuana, you'll find all kinds of evidence about how CO2 can be used to make marijuana more productive. I just wish that it would translate over into to rice or wheat or some of the other cereals. Here's some more data. This was done by Diane Wang. Both myself and Dr. McClung are co-authors on this. But this is looking at the relative seed yield increase. And in addition to CO2, we're also looking at temperature. So the relative increase is the elevated biomass minus the ambient biomass divided by ambient. This is for seed yield. And again, you see the ancestral and the weedy lines showing up as being either more positively affected or not as damaged by higher temperatures. So we think we have this resource to utilize to begin to adapt some of the modern lines. And let me give you a practical example of how that's being done. And this is potato fields in Peru. I mentioned potatoes in McDonald's earlier. What they do is not that they don't grow the same variety of potato, they do. But what they do differently and have been doing for over 3,000 years is around the edge of that plot, they will plant wild or weedy potato, which seems weird, except that they're looking at around the edges for new combinations, new tastes, new disease resistance, new other things. And well, by the way, here's their production for potato, still going up. Finally, let's go into what I call the rainbows, unicorns, and sprinkles solution, new technological, new magic bullets. Well, GMO gets a lot of attention. And you understand that. I mean, to be able to genetically manipulate and and get anything that you want. Wow, that's a powerful attraction. But there's a problem in the sense that, yeah, we've got CRISPR, man. I can move this gene perfectly into that gene. But how many genes does it take to make a really productive plant? 1, 10, 100, thousands? How many genes can I move around and still get the yield that I need to? Evolution has done it. And I can move a few genes around and get some interesting results, but the potential's there. But we're not there yet in terms of being able to mimic evolution in the laboratory. So, okay, potentially it could be very effective. But my fear is that those who say, oh, well, I'll just move a few genes around and our food problem will be solved. No, it doesn't work that way. What about the Haber-Bosch process? I mentioned this earlier, where you take nitrogen out of the air and you make it into ammonia. That's being done. There are big, huge chemical plants that consume a lot of fossil fuels to do this. And it's expensive to move it around. What if we could shrink it? What if we could take miniature Haber-Bosch plants and put them in places like Africa or Asia so that local farmers would have access to it? Maybe that's something to think about. What about biochar? I've heard a lot about biochar. This is you take organic material and you squeeze it and you burn it under low oxygen. It's very carbon rich, and then you add it to the soil and it might help the soil profile and the soil biology, but it's expensive. I mean, if only we had a source of carbon rich material that was cheap, like coal. I know that seems odd, but maybe coal could be the next biochar? Maybe if we ground it up and added it back to the soil instead of burning it up and adding CO2 to the atmosphere, it might help in marginal areas in terms of soil health? I don't know. There are lots of opportunities here to look into areas that have not been well examined. Finally, the issues in terms of research and education. As an academic, you're taught to be a reductionist. You don't take a general view of things. To get your PhD, man, you get deeper and deeper and deeper and deeper into the details. And we don't talk to each other. So we have this issue of silos. Although I think the current administration refers to them as cylinders of excellence. I'm just saying. But we need to break through this. We need to be able to talk to others about climate change, what it means. We need to look for commonalities and science platforms. We need to have access to genetic information and germplasm. We need to have better ag statistics. We need to have better tech and knowledge transfer. All of these things are key to beginning to adapt agriculture and maintaining food security as the climate becomes more uncertain. And finally, just a moment about education and communication. We need to invest in the next generation. When I went to college, there were a lot of agronomy majors. There were a lot of plant phys majors. Now, mostly just genetics. And what's wrong with that? We need to educate and communicate ag science to the next generation. I think that's imperative. How do we do that? How do we had a outreach program here at Beltsville where we brought in students from the inner city. And I cannot tell you the expression on their faces when they pulled a carrot out of the ground or saw a potato out of the ground. They were fascinated by it and really, really interesting. So I think there is a lot of opportunity to do that. And finally, I'm going to say a very biased plug for investment in public research. Our investment at ARS and NIFA, the National Institute of Food and Ag, and the Ag Research Service, has declined over time. In terms of actual dollars, ARS has lost about 25% of its budget. Now, I understand the need to spend defense money. You want to be safe. And so we spend on average, every person in the US spends between $6 and $7 a day
for the Pentagon budget. And you know, if it makes you feel safe, that's great. $6, $7 a day is not a big deal. What do we spend on ag research? We spend 2 cents a day per person. And yet I would argue that investing in public research to sustain and improve ag will have benefits in terms of global security as well, as much as investing in the next weapon system, but we're not doing it. And finally, recognizing that there's different priorities, different means of educating between policymakers and government officials and science. In science, we accept probability. In government, they want certainty. We have a long-term interest. Their interest will end with the election. We innovate. We like to innovate. We esteem innovation. To them, innovation is suspect. All of these differences have to be looked at. They have to be calculated in a way that we can take the science and make policymakers understand what it means. We cannot have a culture where if the science agrees with the politics, it's good science. And if it doesn't, it's bad science. That's not how science works. We need to put the best science, the best logic, the best observations out there and be fair about them and base them on what logic and reason is, not on politics. So now what? We acknowledge the interaction between plant biology, CO2, and global food security. I mentioned the decrease in our budget. All I can do at this point is to provide you with the information that I've done today to get a sense of that the challenges that are facing us in the context of climate and food security are enormous. What can we do together, not in a silo? What can we do together to try and address some of these issues? We need funding, we need resources, we need ways to move forward on these issues. And I would only argue that I think that if we don't do this, that we are going to be asking for trouble, that we are going to be asking for a return back to the 20th century famine as endemic issue.